Hello everyone, I'm Josh Bond and my class project involves an airport simulation. Now in the simulation, we have airplanes that are trying to land at the airport. We have arrivals and departures. We have fewer runways than airplanes, although not necessarily, but that's kind of the point of the simulation. Planes are different sizes and runways have different lengths. So the plane has to fit the runway. So a small plane can land on a long runway, but a large airplane can't land on a small runway. And to solve this problem of airplanes talking to one another and how they interact in this project, I use the mediator pattern. The Gang of Four defines it here for you on your screen. And the mediator pattern keeps objects from referring to each other explicitly. So back over here for a second, you see the airplanes. Do we really want them talking with one another directly? Or do we want them going through a central medium? And that's what the mediator pattern is all about, because in object-oriented programming, we encourage that objects talk to one another. But at the end of the day, sometimes we have too many connections between objects, too tightly coupled. And then every object winds up knowing something else about every other object, which means if you delete one, then, oh my goodness, you have to go back through all the objects and reconfigure everything. That's not good. And this is what that would look like without the mediator pattern, where every in this chat room example here, every user is talking to every other user on a peer-to-peer level, but it's not going through a central medium. And the same thing with planes. This is not going to work very well at all. And this is how it would look when it's fixed with the mediator pattern. Now, rather than the spoked web-looking wheel here, we have everything going through one central medium of control. Plane 5 doesn't need to know anything about planes 1, 2, 3, and 4. Doesn't matter. They don't need to know anything about a runway either. Air traffic control system handles all of that. All the plane needs to do is talk to the air traffic control system, which then makes all of the back-end decisions for the planes. That's the sort of the mediator pattern in a nutshell. This is the simplest UML diagram you will find of the mediator pattern. You have a mediator and you have two objects, in this case aircraft, that are talking through the mediator. And that's how I would define it very simply for you. But the Gang of Four also has their maybe slightly better definition. They call objects that need mediation, they call those colleagues. So a colleague is shown on the right, and then the mediator is shown on the left. Of course, you know that concrete mediator implements the mediator interface, and the concrete colleague can either implement an interface or extend an abstract class. To make it a little more real here for you, you got aircraft here and Boeing 747, 767 on the bottom. Those are concrete aircraft, and they talk back up through the mediator, which is the air traffic control system. The Boeing 767 doesn't talk to the Boeing 747. Say, hey, can I land? Well, I don't know. You got to talk to the air traffic control system. That's the point of the mediator pattern. Now, for the simulation, here's all the rules. We already went over the communication, and the runways are shared, right? So arrivals and departures can happen on the same runway. And the big thing here is aircraft and runways are classified with a classification code called an aircraft design code. Aircraft and runways have this so that we don't have, look on the right side, we don't have a Cessna 172, which needs a 4,000-foot runway. That's not trying to land on a, well, that's not a good example, I'm sorry. Maybe take code E or code D. Code E, right? The Boeing 747, that can't land on a smaller runway because it needs 9,000 feet. And that's the way these work, the least restrictive way possible. So code C, the Boeing 737 can land on a code D or E, but not on a code AB because it needs a longer runway. And where I started here a moment ago, the Cessna 172 can't actually land on any of these runways because, for that matter, Cessna 172 can land in a field. It doesn't need a lot of space. So that's how we'll talk more about the aircraft classification codes here after a while. They deal with the strategy pattern, and we'll talk about that later. Now, we also, as far as rules go, we have some precedence issues here. The arrivals have precedence over departures because fuel is a factor for arrivals. The mediator attempts to respect the order of requests made. So if you request to land first, then the mediator will try to accommodate you, or if you request to depart first, the mediator will try to let you go first. But at the end of the day, the emergency aircraft have priority over all departures. So if there's an emergency situation, the departure will be bumped from the runway to let an emergency aircraft land, and that makes sense. Now, that's not necessarily true for arrivals. Here's the deal. If an arrival has enough fuel to wait on an emergency aircraft to land, and the arrival has enough fuel to then land itself, then the arrival will be diverted and the emergency aircraft will be allowed to land. But if that's not true, if the arrival will crash while it waits on the emergency aircraft to land, well, then we can't do that. We can't save one aircraft only to cause another one to crash. Now, the problem with the blanket statement of, arrivals have absolute precedence over departures is, well, if you keep having a constant steady stream of arrivals, then departures never get to leave. So that's not sustainable. So the way it works in the real world, you can see on the YouTube, if you can't visualize what I'm saying, a departure leaves the runway, and it leaves at one end of the runway. Back at the other end, going in the same direction, maybe less than a minute or so after it leaves, an arrival can then touch down. It sounds risky until you consider that runways are long. And if there is a problem with a departure getting off at one end of the runway, then the arrival coming in will, worst case, be at the other end of the runway. So it's not that big a deal. This is how some of the busier airports share runways. You can't do that with two arrivals. You can't stack two arrivals together and have them approaching too closely, but you can stack it so that the departure is at one end taking off, and then shortly, very, very shortly thereafter, sometimes less than a minute, you have an arrival on the same runway. That's what we do here. If there's a gap big enough, if a departure can take off and there's a couple time units before the arrival comes, then we do it. If the departure is going to impact an arrival, we pull the departure back. It's pretty simple. But none of this changes the fact that emergency aircraft always override a departure, no matter what, even using this stacked approach. Now, the main loop here is a little bit reminiscent of assignment 2. We have a main loop that ticks off time, just like assignment 2. But in this case, rather than vehicles and deliveries, we have arrivals, departures, and runways. A little more complicated. And the loop runs until all of the arrival and departures list is empty. And the list gets empty because crashed, landed, and departed aircraft are removed from the list. And that makes sense because the removal of the list simulates the termination of communication with the air traffic control system. Now, arrivals burn fuel every loop because they're in the air, but their distance is only decremented if they are approaching the runway. If they're just flying around in a holding pattern, their distance is not decremented. Departures burn fuel only after they've been approved for takeoff, and that makes sense because they're starting to taxi and move. And it's decremented once per loop, just like the arrivals are. And we talked about the emergency landings, and just to reiterate, the mediator pattern tries to find a match for any waiting airplane every loop, because so many airplanes can change their status and their intent, and the air traffic control system needs to react to the behavior, to the states, if you will, of the aircraft. Now, this is the main loop, the source code. Not a lot to show you here, just that it's a relatively small loop. Everything's delegated out. Pay particular attention to the state pattern. We're going to talk about that later, but you see we're looping through the aircraft, the arrivals and departures, and we execute a method called fly or takeoff, depending on the flight type, and that executes a state pattern, which transitions the aircraft from one state to another. And we'll get into the state pattern here after a while. You see what I was referring to a moment ago about the landed, departed, and crash designations. Those are removed. And then, of course, we have a lot of display activity, so you can see what the simulation is doing. Now, the mediator pattern, we've already been over this. Just to reiterate, all the communication goes through the mediator, and this is a nice little graphical representation of that. We don't have airplanes talking directly with one another or making decisions on their own about the runways. They only access a runway after they've been assigned that runway by the mediator. And then the strategy pattern. We talked about the group codes. This is how the strategy pattern really reduces the complexity of deciding the logic about what aircraft can land on what runway. You can visualize what a nightmare of if statements and case statements that might be. Without the strategy pattern, we can add more runways, more aircraft quite easily without affecting anything in the mediator, without ruining any code there, breaking anything. It's very flexible, it's extendable, it's scalable. I like it here. It makes sense. And you can see here, just to reiterate at the bottom, about the restrictions on the true underlying goal of these runway and airplane classifications. It's required because, a Boeing 747 can weigh 400 tons on takeoff, but a Cessna 172, no, that can weigh 1,600 pounds. So you've got to have different runways to support these different types of aircraft. And then we have the state pattern. The state pattern makes sense here because an airplane can be in different states, right? There's an initial state that happens when the airplane spawns. Then there's a request state, meaning they've made a request to the tower to land or take off. That request is approved. And if it's not approved, it goes back into the request state. There really is no denied state. It really wasn't necessary. Departed state, landed state, crash state all make sense. The emergency state overrides. It's a little bigger than everything else because it has the potential to override other states. And then we have the abstract factory for runways. Again, I think a perfect fit here. Runways, they're simple enough that they make sense for an abstract factory. We can scale this. We can add more runways. It just gets added to the list that's sent to the mediator. And it shouldn't break any code anywhere else. Then the abstract factory for the aircraft, not quite as good of a fit, but it serves the purpose. I wanted to go with the builder pattern because making these aircraft and the arrivals, departures, that's a little more complicated, and builder works well when you're dealing with a complex object. But here's the problem. I didn't think I had enough time to implement the builder and then do this presentation, the video, all the documentation, the README, the PDF, the diagrams. You can't just IDE generate the class diagram for this. It's unmanageable. You have to filter it in that manually, and it takes time. I didn't know if I could do all of that and implement the builder. I couldn't take that gamble of turning this in late. I would much rather have spent time working on the builder as opposed to perfecting my PowerPoint my PowerPoint skills, which I don't quite value as much as I do the design pattern skills. Now, the singleton pattern, perfect for preemptive bug strikes. Can you imagine the chaos that would happen if the mediator object were spawned twice, and we're passing some aircraft one mediator instance and we're passing other aircraft a different mediator instance? Well, that's going to create all kinds of bugs. It's going to cause somebody to pull their hair out while they figure out what went wrong and why they're seeing bizarre behavior. We stop all of that up front by only allowing one instance of the mediator to ever be instantiated. And then we pass around that one instance. And of course, you see on the screen how it's done. Singleton is one of the simplest patterns that we've been over in this class. The class diagram, let me zoom in on this a little bit. A lot of this, it kind of feels like we've already talked about it indirectly. We've already looked at the mediator pattern. The aircraft over here, concrete examples, go all the way back up through the mediator interface to the air traffic control system, where under no circumstances did the Cessna 172 talk to a Boeing 747. A Boeing 747 never decides it's going to land on a certain runway. This is coordinated through the air traffic control system. And the runway also has the abstract factory, but I don't include it on the diagram because I ran out of room and without crisscrossing lines. And then the abstract factory for the aircraft, we talked about that. It's less than ideal, but this is how it looks. The flight bundle serves both the arrivals and departures, an abstract factory here that they both inherit from, the common code from. Down the left side, left lower corner, we have stat tracker and an input-output class. Pretty self-explanatory. A lot of fields are abbreviated in this view. That's what the little sticky note's all about there. Then we have two of the patterns that really simplify the program, in my view. The strategy pattern, we talked about the group, the airplane group design codes that classify aircraft and runways, and it does so awesomely because I also use the strategy pattern for triggering some of the stat tracker code because we've already got it broken down by the codes of usage, the classification, so it kind of makes sense there. The state pattern, each airplane has a state. And so we see here aircraft has a state, but the colleague abstract class itself has the airplane design group code, which makes sense because remember the aircraft can have the code and the runway can have a code, but only the aircraft can have the state pattern. Makes no sense for the runway to have the state pattern. That's why the lines come across differently, why they're instantiated a little differently. Now, that's it for the, I think I've covered the whole, yeah, it's a big diagram, but I think we've gone all the way through it. I was going to show you the source code, but I don't think I have enough time. I think I'm way over as it is. But let me show you output of the program here because, you know, a picture is worth 1,000 words. Wish I had a GUI to show you, but if we had a 16-week class, I could probably put one together with really an overall better program. Here's the runway assignments. Nothing is on the runway because the program just started. Nothing is approaching because the program just started. And nothing is taking off. You can guess why, right? Program just started. A lot of fuel on takeoff, not so much when you're coming into land. Makes it interesting. And then you have all the requests to the tower, right? This is Southwest 2726 talking to the tower. Can I land? Yes, you can, right? Goes all the way through. I made an interesting situation where this flight here, private flight 557, which is probably going to be like a Cessna, needs an emergency landing. So we look for someone to bump off the runway, and just so happens we're going to pick on this Southwest flight, make them move out of the way because they have enough fuel to do it, or the request would never have been granted. All the way through it goes. There's a status each time. Did anything land? Anything depart? And these are the runway assignments. Remember, we talked about the arrival and departure on the same runway. If there's enough time between it, plenty of distance here. 13 units out, and we only need 5 to take off. Difference of 7. That's actually much more padding than you get in real life. So down here toward the bottom, this goes on and on and on. We're not going to, don't worry, we're not going to look through all of this. End of simulation stats, 4 arrivals, 4 departures, 0 crashes. So we know we haven't overloaded the system because there's no crashes. I think I have it so that arrivals or departures, well, there is no crashing for departures in this simulation, but if an arrival crashes, it doesn't show up. If there was a crash down here, it would show up as 3 because it never truly arrived. And so it would show up as 1 crashed airplane. And yeah, that's my project. And I'm sorry don't have enough time to show you the source code, but I think you get a good idea of it. And I thank you for watching.